So last time we talked about the Schrödinger's. We finished more or less here. So we talk about a very difficult concept called the wave function. Wave function try to describe the behavior of a particle, usually a very small particle like electron. Uh, and actually, so far you don't know why it can be separated into the spatial term and the time dependent term. But just as I did first, I'll let you know in the supplementary note. And the time dependent term is exponential to I omega t. So so we can have the time independent Schrödinger equation like this, and without any potential function or potential energy, we will get the solution for the free particle. And if we consider one-directional solution, it will look like this. And one point I forgot to mention is that the total wave function, maybe xt. Here we only consider the one-dimensional case, which will be equals to phi x exponential to minus j or I omega t, because I usually use j rather than I, but sometimes I can write I, but usually I will write j. So here we have phi x like this, so it will look like exponential to j kx minus omega t. So if you still remember in chapter 33, the EM wave, when we solve the wave equation, actually this one is the solution for the wave equation, and at that time we call it the plane wave, 平面波. So this is a very important. This is a very important concept in quantum mechanics or in the Schrödinger equations. So it will look like this. So last time we stopped at here, which is the Heisenberg uncertainty principle. So in the textbook, the version is like this: delta x times delta px is larger or equal to h bar. The textbook look like this, so there are some examples, so I don't really change it, but more rigorously, you can find it. It will look like something like this: sigma x, sigma p larger or equal to h bar over 2, or delta x, delta p larger or equal to h bar over 2. So there are a factor of 2 difference between them, but I keep it here. Actually, if you have more, if you have rigorous definition and rigorous math, then actually it should satisfy this, because this is a stronger condition. This is a stronger condition. But at that time, Heisenberg really proved this version first. But later, maybe some other person push it to h bar over 2. But it is not a great deal at this moment. But here the point is there are actually two interpretations for the Heisenberg uncertainty principle. One is that if you measure the position of a particle and measure the momentum of a particle in x direction, for position and momentum, you will have error. You will always have error. You cannot measure the position and the momentum or it can be equivalent to the speed or the velocity of the particle. You cannot measure both of them accurately. If you get this very accurate, then the error of the momentum will be large, and vice versa. So these two error terms must be larger than a constant h bar, or more rigorously h bar over 2. And another interpretation is that when you try to measure the position or measure any physical variable of the particle, then you will really interfere it, which means that if you try to measure the position of a particle, and then you try to measure the momentum of the particle, you'll get a result for the position and the momentum. For the next case, if you measure the momentum first and then you measure the position, then the result will be different, which means that when you try to measure it, you really disturb it. It is related to the Schrödinger's cat, which you may heard before. Before you really measure some variable about a particle, then you just like a probability wave. But as long as you try to measure it, it will collapse to a state. And actually, you can have some other interpretation about it. So let's just consider the free particle, which we have derived in the previous page, so you may have some idea about it. So at that time, when we solve the Schrödinger equation, the time-independent Schrödinger equation, then we'll get this wave equation, which means that here we'll have so this is the x-axis, and this is the absolute square of the wave equation, which means that this is the probability that the particle exists in the space. So in this case, as this one is constant, phi 0 square. So actually, you can consider that you don't really have too much information about the position of the particle. So in this case, you can consider delta x is infinity, because you have no idea where it is. It may be here, it may be here, or it may be there. All the probability are the same, so you have actually no idea. So let me ask you, what is the wave number of the particle for a free particle? Wave number k. Wave number k. So if I try to plot it in the k domain, actually, because you know phi x is exponential to ikx, which means that only k is possible, which maybe we can write it as k prime as the axis. So in the k domain, it is actually a delta function, delta k prime minus k. So all of you have studied the signal and system. So in the supplementary note, I'll tell you that in X domain and K domain, they are Fourier transform pair. Fourier transform pair. So you have studied the Fourier transform constant or exponential. Let it be 1 first. If a function is 1, then the Fourier transform will be delta function at the original point. But here it is a exponential to ix, so the delta function is shift to k rather than at the original point. So these two are Fourier transform pair. And in this case, what is delta k? Delta k will be 0. Delta k will be 0. Delta k will be 0. So actually you want to know p. So what is p? What is p? P, you know, p is h bar k. H bar k. So delta p will be h bar delta k. So as long as the wave number, you can get it very accurately, the momentum you get is also very accurate. However, the delta x will tend to infinity. So this is an extreme case for this one. You get a very accurate momentum. However, you will totally get lost for the position. And then let's try another case, which is the normal distribution. And this is actually the case that Heisenberg has proved delta x delta p is larger than h bar. So the case is something like this. So I'm not sure whether you know the normal distribution or the Gaussian distribution. So if you assume that the phi in the k domain is a normal distribution, which means that it will be equals to say, square root of 2 pi sigma k on the bottom, exponential to minus 2 sigma k square, and then k prime minus k square. So this is the normal distribution. This is the normal distribution. In a graphical way, it will look like this. It will look like this. It is a bell-shaped Gaussian distribution. And the standard deviation of this one is sigma k. Yeah. And the middle point is k, and this is the k prime axis. So what is the phi x? Phi x will be the Fourier transform of phi k bar, which means that you transform it from k prime domain to x domain. So calculating this Fourier transform is not really difficult. So you just write out the definition, and this is a bit different from what you learn in signal and system, because in different textbooks the definition for the Fourier transform usually different. I have read at least three or four definitions for the Fourier transform, but they are more or less the same, only some different. Maybe for this time here, because it tried to make it fulfill the Parseval relation, which means it don't really have a 2 pi factor. So sigma k square and exponential to minus ikx dk prime. So dk prime. Could be something like this. Which means that for this one, you don't really have very accurate information for the particle, but the error is not really large because sigma x is sigma k is finite. It's the standard deviation of this one. And with some maps, you will be able to find it. The Fourier transform of a normal distribution is also a normal distribution. And actually, you can really calculate the simpler version. Let me make k to be 0. Let me make k to be 0. So this term will be something like k prime over 2 sigma k squared. And this is a shift in k prime domain, so that in the answer you multiply the exponential function, then it will be the correct answer. But here, make it something like it will be simpler to calculate. And actually, there is a square here. There is a square here. So to calculate it is not so difficult. You only need to complete the square. So I don't really write it here. I have shared it on the UM model already. And actually, you can just make it complete the square because you have a k prime square term. You have a k prime term. So that you add the constant term and then minus another constant term. Then you will complete a square, and finally you will get something. You will get something like this. Just a couple of steps, so it's not so difficult. And you'll find that it will be something like this. Sigma k square x square 2 and this one exponential to minus u squared du. And I'm not sure whether you have learned this Gaussian integral in the math class. This term is actually square root of pi because you can just simply assume it to be like this. U is a dummy variable, so it can be dx or dy or dz, whatsoever. So we can make it something like this. We calculate the square of this integral, and then we combine them together, and then we change it to polar coordinate. So we have r equals x squared plus y squared square root, and theta equals arctangent y over x. Then you have something like 0 to 2 pi d theta, and integrate this one from 0 to infinity, r exponential to minus r squared dr, something like this. So this one is 2 pi, this one is 1/2. So finally you get pi, and I squared is pi, and I should be positive because this integrand is positive, so I should be positive. So we finally find that this integration is square root of pi. And actually, the main point is we find that the Fourier transform of a Gaussian function is also a Gaussian function, but this one is the standard deviation or the variance term if you consider the sigma k square is the variance term. If you only consider sigma k is the standard deviation. So if sigma k is larger, then the Gaussian distribution will be flatter. If sigma k is smaller, then the Gaussian distribution will be more concentrated. But here you observe that sigma k square is at the bottom for the k domain. But here sigma k is on the top for the x domain, which means that the standard deviation of x is actually 1 over sigma of k. So this is very important. Characteristic. And finally, you will find that I'm not sure. Let me add another page in between. So we know that sigma x is actually 1 over sigma k, and also we have p equals h bar k. So sigma p is also h bar sigma k. Here we'll have sigma x sigma k equals to 1. Equals to 1. So sigma k will be h bar sigma k, h bar sigma p. This one should be sigma p. Sigma p. The standard deviation of the momentum. So, or you can write it as sigma k equals to sigma p over h bar. So we substitute this one into here. We'll have sigma x, sigma p over h bar equals to 1. So finally, sigma x, sigma p is actually h bar. So this is what Heisenberg has proved for the Heisenberg uncertainty principle. So you can consider something like this in the x domain. If the in the x domain, if the particle is distributed in this with this distribution, which is, for example, if the standard deviation is very large, then you get an accurate information for the momentum, or vice versa. If you really get a accurate x, then you get a not accurate p. So this is the meaning of the Heisenberg uncertainty principle. Actually, this math is not so trivial, so let us go back to the sample problem, which is easier. You just only need to substitute value into the delta p delta x larger than or equal to h bar. So in this example, assume that an electron is moving along x-axis that you measure its speed is something like this, which can be known to be a precision. So precision, which means that the error is 0.5%. What is the minimum uncertainty of the position? So now px is mvx. So this is a classical way to consider it, because the speed 2 times 10 to 6 is much smaller than the speed of light, 100 times smaller. So we can ignore the relativistic effect here. Okay, so for an electron, the mass is 9.11 times 10 to minus 31, and the Vx is given to be 2.05 times 10 to 6. So, which is actually 1.87 times 10 to minus 24 kg m s inverse. So delta px is nothing but 0.5% times px, which is 9.35 times 10 to minus 27 kg m s inverse. So delta x will be h bar over delta px. Or maybe you can write larger or equal to. Although here it asks you the minimum uncertainty, so that maybe you can write mean here or whatever, or just leave it delta x is okay, I think. So h bar is h bar should be 6.63 times 10 to minus 34 over 2 pi. And delta px is 9.35 times 10 to minus 27. So the answer is 11 nanometer. So actually the uncertainty for a electron is around 11 nanometer. So that if you get a precision which is has a larger error, then delta x can be smaller. And if you get the momentum even more accurate, then the error for delta x will be larger. Any questions?用的是你说哪个？这个就是这个，就这个。就是没有那个大于符号，或者是我写 minimum 就是大于等于。So let's continue. So there are two interesting phenomena for the quantum world. The first one is the potential step, the reflection from the potential step. This one is very interesting. So suppose in the real world, suppose there's a bird flying. So assume this is a bird and it is flying in this direction. If this is flat, then it shouldn't be any problem. If there is a mountain so high, then there will be a problem, right? However, if the hill is not so high, if the hill is something like this, suppose it fly higher than the mountain, then there shouldn't be problem in the classic world. In the classic world, should be no problem. This small hill shouldn't influence this bird. However, in the quantum world, it really have problem. It really have some influence for the particle. Here we consider there is a potential step, something like this. If the electron has a higher kinetic energy than this potential energy, in the classical world, the electron can really go through it without any obstacle or without any block by this potential step. And we make it a perfect step so that the calculation will be easier. The calculation will be easier. Here, you can imagine the case like this. There are two wires. The two wires are not connected together. So for the left one, it is connected to a voltage V equals to 0 or a ground. But for the right hand side wire, it is connected to another voltage VB, which is smaller than 0. But this one is a electron, which is a negative charge, so that UB is E minus E VB. Sorry. Minus EVB, and VB is negative, and this is negative. E is positive, so this one should be larger than 0. So we have a UB larger than 0 like this. And if the kinetic energy of the electron is large enough, then it will really influence by this block, by this step, I mean. So actually, the transition is called the potential step, potential energy step. The step is said to have a height UB, which is potential energy, and electron will have once it pass through the boundary. So actually, it will be reflects. It can be reflected by this step. So we can go back to the Schrödinger equation, the time-independent Schrödinger equation. And for the left-hand side part, for the region 1, this is called the region 1. Region 1 for the x is smaller than 0. This is region 2, which is h larger than 0. So for x smaller than 0, UB is, U of x is 0. So this Schrödinger equation is nothing but second partial derivative of phi with respect to x plus 2m over h bar square e equals to 0, something like this, times phi, because u of x is 0, and this is nothing but the previous differential equation, and actually we'll get the same plane wave solution for region 1. So actually we consider both the positive direction and the negative direction terms. And for region 2, we have u equals to ub, which means u of x equals to ub. And here we also assume that E is larger than ub. So that this term is still positive. And this is also positive. So the whole term is still positive for region 2. And actually, we can also get a similar expression for phi 2 in region 2, although KB is a little bit different because this time UB is not 0. So actually, solving this second order ODE, KB will be something like this, and the phi 2 will look like this. So here we are assuming that the electron is going from region 1 to region 2. So the probability of the electron refracting is exists. So we'll let A, B to remain here. However, for region 2, as long as the electron going into region 2, we did not expect it to go back. So we'll assume that D will be equal to 0. So here, phi 2 will be only C times the exponential to IKBX without the negative direction term. And actually, we need to guarantee that the wave function is continuous at the boundary, and also the first derivative is continuous at the boundary. So first of all, we make the wave function to be continuous at the boundary, which is 0 in this case. So we just substitute 0 into here, substitute 0 into here and 0 into here, and then exponential to 0 is 1, exponential to 0 is 1, exponential to 0 is 1. So A plus B equals to C. We'll get this equation. So next, we also consider phi prime is continuous at the boundary or at any point. Actually, the and at the whole x-axis, phi and phi prime is continuous. So we take the derivative of phi 1 and phi 2 and substitute 0 into it. So we will have this one ik times a for the first term minus ikb times this term. So we'll have minus bk, and actually all the I are cancelled. For this one, it is CIKB, and so I all cancelled. So here we have KB, and this one substitutes 0, so the exponential term disappeared. So we have another equation for the boundary condition. So we have totally 2 equations. One is for the wave function to be continuous. One is the first derivative of the wave function is continuous. So solving these 2 equations, we can know that the probability that the particle is reflected is B over A, take the square root, take the absolute value and then square. Because it is B square is actually the probability that this term, which is going to the negative direction, and actually you should remember that. This term, absolute square of the wave function, is the probability that the particle is the probability density function of the wave probability density of the wave function, probability density function of the particle, I mean. So if you really want to consider what is the probability that particle is reflected, you can consider something like this, which is R equals to B exponential to minus IKX over exponential to IKX squared. So the upper term is the wave function correspond to the particle going backward, which means that it is reflected by the potential step. This term is the wave function correspond to the particle going into the x positive x direction. So we take the absolute and square, and so this is the ratio between the probability that the particle will going backward to the going forward, and this term, the square root, the absolute value square will be 1. This one is also 1. So the remaining term is b over a and take the absolute value square. So we can, using these two equations, we can eliminate c, so that we'll find that R is something like this. K minus KB over K plus KB all squared. So this is the reflection coefficient defined here. And similarly, the transmission coefficient is nothing but T equals to 1 minus R, because totally the probability is 1. So part of it is reflect, and the rest of it can transmit over the potential step, which means here is that even though the electron has a higher kinetic energy than the step, it has some probability that it will reflect by this step. So it is very interesting phenomenon. And in next semester in the electromagnetism, you when you learn about the transmission line theory, you have something like this. You have some formula like this. So next, okay, maybe let's have a 10 minutes break.